Okay, we are talking about this example. We have this two-tank system with 3 valves, and I just noticed that actually I use U1 here and then use the U2 and then I name that valve 0. It's a bit it would be a bit confusing because at some point we have U1 because here we have U2 but we have Q1. We haven't used U1, U2, U3 yet. It would be actually difficult for me to change this Q1 to Q2 and Q2 to Q3. If I would do that, actually it would help. But yes, I think it would be a bit, or maybe I can do that. Let me rename this instead of Q1 because it would be not consistent. We should change one of them. You should change either this one to U1 or this one to Q2. So I will change this one to Q2 and this one to Q3. I need to go to the equations and take care of that. So Qi minus Q2 and Q2 is H1, that one is correct. So we have substitute that, so here it's okay. Yeah, that one is also okay. But this one, instead of R1, because yeah, here we should have also R2 because it's the resistance of valve number 2. So this one should also be R2. Then I need to come here, change this one to Q3. And this one would be Q2 minus Q3. And this one is R3. So again, R2, 3, 2, 3. Is that okay? I just change everything just to make sure that it is consistent with what we have or what we named the valve and also the flow rate. So this one is Qi. Also, we can change it to Q1 to be consistent with that one. It's just a matter of writing this Qi as Q1, and that's it. Okay, sorry for this, but during the break, I was actually thinking that if we do it, it would be actually easier to continue. Okay, that's the model we have. So let me summarize it here. We have these two equations. H1 dot is equal to minus 1 over R1 A1 H1 plus 1 over A1 Q1. And the second equation is that H2 dot is equal to 1 over R2 A2 H1 minus 1 over R3 A2 H2. Okay, but if you want to see what the input is, so for a valve like this, when you change U1 or U2, basically you are changing the resistance of the valve. Okay, so as I mentioned, usually it's like that. When U is 0, the valve is completely closed, and when U has some value, it could be completely open. So the way we can model that, it would be actually like this. So model of a valve. So Q, for example, for this one, Q1 is equal to 1 over U1. In principle, it's alpha divided by U1. Sorry, R1, sorry. R1, the resistance of the valve. The resistance of the valve is alpha over U1, which means that if U1 is the input to the valve is 0, the resistance is infinity, therefore the flow rate is 0. So the resistance is alpha divided by U1. If you do that for all valves we have, and also if we assume that the valves are the same, so we are using the similar valve for all of these 3 locations, which means that this alpha for all valves would be the same. So I will go to the equations. Wherever we have R, I will replace it by alpha over U1. So, and for simplicity, let's assume that alpha is equal 1. Assume alpha is equal 1. So R1 would be easily 1 over U1. Therefore, what we have, it would be H1 dot is equal to, also let me assume that A1, the area of the first tank is 1, the area of second tank is 2. So I'm going to replace all of them. So H1 dot is equal to minus, so we are supposed to have it from here. It would be U1 H1 plus, and then Q1 is, okay. I need to also mention something here, because the first valve we have here, when we say Q1, we need to know what is actually the level of water in the left side of the valve. But if it is actually the input valve, usually the tank we have in the left side, we maintain the level. Therefore, the level is always constant in the left side. Because of that, I can assume that it's a constant value. So that constant value, I can assume that it is 1 as well. So I assume that Q1 in principle is the level of water here minus 0 divided by resistance, but I assume that the level of water here is 1. Therefore, it would be easily 1 over R, and then 1 over R, I need to replace it by U. So it would be, sorry again, I needed actually to change this one to R2. So if this one is U2, this one is U1. So I changed a lot here. So H2 dot is equal to, so U2 divided by 2 multiply H1, and then minus 1 over 2 multiply, so U3 H2. So it's something like that. So this is the equations we have. We have 2 states, H1 and H2, and we have 3 inputs, U1, U2, U3. Okay. So if you couldn't follow, just notice here that we have a system that has 3 inputs, U1, U2, U3, and it has 2 outputs, H1 and H2. But the system is nonlinear. Okay. So even though we assume that the model of the valve is linear, but because we have multiplication of input and state, we have a nonlinear model. So what I'm asking you is to model this system in Simulink, also you to linearize that, and then we try to design a controller for that. Or maybe I can linearize the model here as well. So let's linearize it here, and then we go to the simulation. So if we want to linearize the model, we need actually to assume that what is the working point we want to linearize. If I go back here, so first of all, I assume that all valves are the same. And if all valves are the same, then whatever level we have here, if you wait enough, the level in the second time would be the same as the level in the first time. Because the permanent value for the level of water is actually a function of, only is a function of the inflow and outflow. So, and if they have the same valve, it would be actually a function of the valve parameters because the valves are the same. So whatever level you have here, you will get the same level here, the same permanent level. So I assume that the working point we have 1 meter here and 1 meter here. And also I assume that the valve is half open. So for the valve, I assume that we have U1, U2, U3 is equal to 0.5. So working point, U1 is 0.5, which means that, for example, the valve is half open, 50% open. U2 is also 0.5, U3 0.5, because they are open, they are 50% open. Therefore, what we get here for the level U1, okay, H1 is 1 meter, H2 is also 1 meter. So let's see if this working point works in the equation of the system. If you have U1 equal to, just give me a second, I will be back in 1 minute. If you're wondering how I have found this working point, you know that working point, or what we call it in nonlinear system, equilibrium point, is basically when the derivative of the state variable is equal to 0. So the left side is supposed to be 0. Okay? And if I tell you the valve is half open, all of the valves are half open, so 50% open. So U1, just notice the first equation. U1 is 0.5. Left side is 0, U2 is also 0.5. What we get for H1 is 1 meter, because it's only the only case that you could have 0 here. So these three are given, U1, U2, U3 are given, and H1 and H2, we should actually find it from the equilibrium point. So H1 would be 1 meter, and to find H2, again, H2 dot should be 0. U2 and U3 are both equal, and they're equal to 0.5. So you see that actually H1 should be equal to H2. H1, we found it already from the first equation. It was 1 meter. Therefore, H2 is 1 meter as well. So this is how I found the equilibrium point. You can assume different values for U1, U2, U3. You can substitute here, set the left side equal 0, and find the equilibrium point for the levels. Is there any question here? Just feel free to ask, because you're supposed to simulate the system and design a controller. If you have any questions, just ask here.
No questions so far.
Okay. So if it is the working point, then we need to linearize the system. So I will do also this one as well. To linearize the system, you know that you should take the derivative of this right side with respect to H1 and set the values as is given here. So I will write it without intermediate step directly the final answer. So H1 dot. So derivative with respect to H1 is minus U2, and U2 is U2 is 0.5. So it would be minus 0.5 H1, and derivative with respect to H2, there is no H2, so nothing here. And derivative with respect to U1 is 1, so plus 1 multiply U1, and derivative with respect to U2 is H1, and H1 is 1, therefore it would be minus 1 multiply U2. Okay, this is what we have for the first equation. The second equation, if you again you take the derivative with respect to H1, it would be U2 over 2, and U2 is 0.5, therefore it would be 0.25 H1. Derivative with respect to H2, it would be minus U3 half, so it would be minus 0.25 H2. Derivative with respect to U1, there is no U1, so it's 0. With respect to U2, it's H1 over 2. So it would be plus H1 over 2 and H1 is 1, so it would be 0.5 U2, and finally it would be, with respect to U3, it would be minus 0.5 U3. So if I write it in a matrix form, H1 dot H2 dot is equal to minus 0.5, 0, 0.25 minus 0.25 multiply H1 H2 plus U1 U2 U3. We have 3 inputs, so plus 1 minus 1 0, because you have U1 minus U2 and nothing from U3, and here you have 0.5 U2, so it would be 0, 0.5 minus 0.5. So finally we got that. Is there any question?
That's pretty good.
Okay. So what I want you to do is to, maybe we can only simulate the linear system in MATLAB. So we simulate this system, and what we do, we design, for now, we don't consider U2. We only use valve number 1 to control the level of water in tank number 1. And then we use valve number 3 to control the level of water in tank number 3. And just use a ready block PID in MATLAB, because I want to show you what happens if this fault happens. Then we need actually to switch to the other control, to the other valve. But something happens, some transient response happens, and I want you actually to see that, because today, as I mentioned, today is mostly for introduction and also to show you, even though on paper it seems quite straightforward, when a fault happens in this valve, we switch to the other valve. But by switching to the other valve, something might happen, some transient, unwanted transient response. And then next week or the week after, I will actually explain you how to avoid that transient response. But here the idea is to simulate the system and see what happens. Basically, what we do in the controller, we say that the controller should be reconfigurable. Always in fault tolerant control, we have reconfiguration of the controller, which means that you have a control loop for, let me also explain you what you're supposed to do in the simulation. So what I'm asking you is to only consider U1 for the level 1 H1 and U3 for now for the level 2 H2. Okay, so I'm asking you to design a controller here. So you compare with the set point and the set point, because the working point, we assume that the working point was level was 1 meter, but you can, for example, you could have it, for example, a pulse signal that goes between, for example, 0.8 and 1.2. So a pulse signal that changes like that. And then you have a controller here. You can use a PI controller. And this is U1. So basically we are using U1 to control the level of first tank. And here we use U3 to control the level of second tank. And what I'm asking you is to basically design a control loop here. Let's assume the same parts generator, but not exactly synchron. So this one also goes or changes between 0.8 and 1.2, but not synchron. Let's have them not synchron because we want to see the interactions if there is any. So I plot the same parts, but I plotted the 1.2 first just to show that they are not synchron. And here is 0.8. And there's another controller here to take care of the level here. Okay. What we have here, basically, we have the overall system. So let's plot it like this. So this is the plant, and there is an input here reserved. We are not using that for now. So design a controller. Let's get that work and tune the parameters of the controller such that it is working. And later, I will tell you how to do or how to simulate the case that this fault happens. Okay. So I will give you time. Try to do that, to do this simulation in Simulink and try to get it to work. And then later I will tell you how to proceed. So maybe I can stop record. Okay, we need actually to bring this state space. Try to do it fast. Just let me know if you have if it doesn't make sense. So the A matrix I have given is minus 0.50, 0.25 minus 0.25. So this is the A matrix, and the B matrix is 1 minus 1 0 0 0.5 and minus 0.5. What is C matrix?
So identity matrix.
Yes, because we assume that we are measuring both levels. And what about D? Basically, D should be 0. I'm not sure if we set 0 here, MATLAB is okay with that or not. Just it's a matrix 0 because there is no direct relationship between the inputs outputs. That's how I did. So okay, so that's the model. So I will use a multiplexer because the system has 3 inputs. And a DMUX. And the first input we name that U1, and then U2, U3. And the outputs are H1 and H2. If you make a subsystem here, so that's the system. And we are supposed to design a PID controller. So bring just a PID block here, connect it to the first input. As I said, the set point, I use a parse generator. And the parse goes between, okay, the amplitude of parse is supposed to be 0.4. Period, I think 10, maybe 20. And parse width 50%. But this one goes between 0 and 0.4. It's not between minus 0.2 and plus 0.2. I will correct that. But let me, okay, let me connect the, oh my God. MATLAB is trying to be so smart. No. Okay, let's do it that way. Okay. So this is H1. So I will not design the second one for now, and I need actually a bias term because, as I said, the parts generator is changing between 0 and 0.4. I need to subtract 0.2 from that. So let me also add a dashboard scope here. So this is R1. And this is H1 also. I haven't tuned the controller, but I increased the final time just to show you that it is it's going between 0.2 and minus 0.2. So we have controlled the first level. Is there any special thing about the second loop that I'm going to design? Actually, there is, but I want you to find that special. There's a difference between the controlling here and over there.
But that's dependent on two, isn't it? That's a different difference.
You mean the difference that I said they are not synchronous? Is it what you said? I mean, when I design it, okay, let me do that. So I will copy the set point here, but I will shift it because as I said, it's better not to be synchronous. So I go here and then we have this phase delay. I use 5 seconds delay, for example. And this one is R2.
Can you say why you added the bias block again?
Because the parts generator changes between 0 and 0.4. When you set amplitude to be 0.4, it is between 0 and 0.4. I wanted to change it between minus 0.2 and plus 0.2. That was the reason. But it doesn't change anything. But does it make sense what I said? Because I wanted that the original set point, remember, the original set point was 0.8 and 1.2 meters for the level. But because we are working with the linear system, we need to subtract the working point from the reference. So the set point for the linear system is minus 0.2 and plus 0.2. So I will add another dashboard scope here for the second one. I need to deselect this and then select R2 and H2. Let's name it H2, then the name appears here. So if I run, what happened? Okay, I think I forgot to. Yeah, okay. If I run, you see that the second loop is unstable. Do you know why? Obviously, here we are talking about the fault tolerant control. We are supposed to talk about fault tolerant control, but if you don't know the system exactly and the issues that you might have in the system, I mean, part of the fault tolerant control is to design a nominal controller for the system, for the faultless system. Because of that, what I'm saying here is actually makes sense. So it makes sense to spend time here and think about that. Why, for example, this one is unstable. the camera is still open. So this is the plant. So if the level is less than, if the second level or the level of the second tank is less than set point, what should you do in terms of U3, in terms of the valve number 3? If the level is less than set point.
Should close it so that
Exactly.
water can rise.
Exactly. But if you think about the first system, I'm pointing to the figure. The camera is open. So if you look at the first system, when the level of first tank, is less than set point for the first tank, you should open the first valve. But it's actually the opposite for the third valve, because the third valve is at the output, not at the input. Does that make sense? So the controller you design for the third valve is not the same for the first valve. What to do? Do you know? Any idea?
Divided by the
Should
second
be the inverse of the signal.
Yeah, exactly.
Close
If you
it.
multiply it, for example, by -1, I actually like to have this gain here separately from PI. It could be, of course, inside the PI, but to emphasize that, I want actually to have it here. I'm not trying to fine tune the controller, so because we can do that. We can fine tune the controller and make it actually work better, less overshoot, for example, faster response. It's not what I want to do. It's not the focus of our work here. The focus is actually to design two controllers. Now we have designed, so we are able to control the second one as well. Okay, so now we are controlling actually the both levels. And you might ask why a PI controller, why not P? For example, for the second one, actually P might also work, but the point is that we may have some disturbance as well, and the disturbance could be a leakage or could be an evaporation. Let's say if we have the tank outdoor and there could be an evaporation. So because of those disturbances, having a PI controller actually can take care of those issues as well. So the point here is not, I'm not going actually to convince you why PI or something like that. The point is, a fault happens. And when a fault happens, the functionality of the valve number 3 is not working anymore. Okay, so if it is not working anymore, you want to use valve number 2 to control that. So not working for the valve number 3, let me keep it open. So and by the way, I need to also check what the signal here is. Let me have another one of these dashboard score. And here I'm going to let's plot U1 and U2. So U1 and U2 actually they're changing between, let's say, 0.3 and -0.3. So I can go here and so a manual switch. So basically, we can actually assume that there is a fault here. And the valve gets stuck at one position, and this position is 0.3. So I switch to this 0.3, and let's go back and see what happens here. Yes, because the valve is always open, the level of the third tank, it keeps decreasing. Remember that this level needs to be subtracted from the equilibrium point, which is 1 meter. So basically, this 0 here means 1 meter for the level, because this is the level in the linear system. So it keeps decreasing. Okay, it's not working, and yeah, U2 here. Yeah, okay. So this one, because inside the block, I use this switch to switch to this faulty situation. So when I switch here, actually we are having a fault. Now I give you time to design a controller for the second tank using the second input. Okay, keep it as it is. Okay, you don't have this block diagram, do you? Are you repeating what I'm doing here?
Yeah.
Okay, then please spend some time to design a controller for the second tank using input number 2, and then we actually switch between the controllers. When the fault happens, we switch to the controller that we designed using U2. So I give you some time. I will stop recording, and when we are back, I will record again. So I'm recording again. Let me also continue here. So
I'm sorry, what is that block that you used after pulse generator?
bias.
Yes. Okay.
So I'm going actually to design a controller for the level of second tank using the second valve. So I'm using a PID controller, but because the second valve is basically the input of the second tank, you don't need this negative sign. So I'll do like this. And the set point, because the second valve is supposed to control the second valve, therefore the set point would be the same as the set point we use for second valve, for the second tank, sorry. So I'm using the same set point here. I need actually to go inside and switch to the other one, which means that the valve number 3 is not working. And so now I need to run the simulation. So you see that it is actually working. This, the second one, notice here, it is working. But using the second valve for controlling the the level of second tank, it does affect the level of first tank as well. If the camera is still open, you can notice here the second valve is having some effect on the level of first tank as well. Is that clear? So when you get it to work to control the level of second tank, it does affect the control of first tank. So the PID is not well tuned. You would get better results if you tune the PID. But as I mentioned, it is not actually the point here. We don't want to spend too much time for tuning control. It is actually trying or testing the idea of fault tolerant control. So I will I'll change the period of the signal just to make it a bit easier to control. So now I run and explain what happens. Okay, we are using the first valve. This is the first valve for controlling the level of first tank. But okay, it has been controlled somehow, but at some point, because you have changed the set point for the second tank, and you're using the second valve for controlling the second tank, and second valve is the output of first tank. I don't know if you can see both the Simulink and the camera at the same time. Let's see if I can do it here. No, it's not. Okay, I think I made it. Okay, I think now it's better. Okay, we have both here. If you notice here, we are using this valve for controlling the level of the second tank. And at this time, when time is 10 seconds, then we have changed the set point for second tank. So when you change the set point for second tank, you want to increase the level of the second tank. Therefore, you need to open the second valve. But opening the second valve means that actually you decrease the level of the first tank. It is a MIMO system. When you change the valve opening of the second valve, of this valve, it does affect the level in the first tank. So the level has been kind of controlled. So it has been controlled, it has been settling down on 0.2, but not because you want to take care of the level of the second tank, you open this valve to increase the level. So opening the valve decreases the level in the first tank, but eventually it comes back, and if it's settled down there, okay. So it will work. So as I said, maybe even I can give it enough time. So 200 seconds, and I can change it because I don't want you to think that actually it is actually quite normal that happens in the MIMO system, and that was actually the reason I asked you not to select the set point or the reference to be synchron, because I wanted to show you the effect of second set point on the first one. Now I have given more time. So this is the level of first tank. It has been controlled. Now at this point, we have changed the set point for the second valve, for the second tank. And because we are using this valve, so opening this valve, as I said, it will actually change the level of the other one. But the point is that it is actually being controlled. So we have been able to control the level of both tanks using valve number 1 and 2. And if I disconnect this valve number 2, remember inside this block, I have also switched this valve number 3 off. So in this case, if you run the simulation, then the second valve is not being controlled. So
You paused the simulation.
yeah, okay. Continue. Okay. You see, you cannot control the level of the second tank. But if you switch this one on, now you are able to control both. But this time actually the interaction is less, and the reason is that we are not using the second valve, because second valve is having direct effect in both levels. We are using the first valve and the third valve, and first valve is for controlling the level of first tank, and third valve for the second tank. Because of that, we are getting a better control because the interaction is less. It's actually the case in MIMO systems. If we want to design SISO controller, because the controller you have here is SISO, you're using, you're comparing the output with the set point, and error will change only one input. In case of MIMO controller, you compare both outputs with the set points, and both errors, so this error can change the other one, the other error can change this one. But for a MIMO system, we have designed SISO controllers. If it is the case, we prefer actually to find inputs that has dominant effect on the corresponding output. So this selection of inputs is quite understandable. It does make sense why we have selected U1 and U3 and why we have avoided to use U2. But in case a fault happens, then actually we need to have a backup plan, and the backup plan is to use U2. I just showed you how it works. And also I'm interested now to see what happens if we have everything. So it's interesting actually that we could have U2 and U3 both at the same time. Okay, so now if you switch the valve number 3 off, still it's able to work. Okay, so the point is that you need to reconfigure the controller. What does it mean? It means that you need to have a supervisor to check whether or not a fault has happened. So we need a block to, first of all, to detect the fault, and then to isolate the fault, and then to diagnose the fault. So we need to find if a fault has happened. So I will talk about that maybe in 2 weeks. We spent 2 weeks on talking about how to realize a fault has happened and which kind of methods we have to find if a fault has happened, and to isolate and to identify and actually understand where the fault has happened. And then when we realize that we need actually to do some change in the controller, but changing the controller is not changing the parameters. Remember, in control, we also have adaptive control. For example, you have designed a controller for a crane system. In the crane system, because the crane can pick different loads. It could be, for example, 100 kilograms, or it could be 10 tons. The controller you design for crane from one load to another could be actually different, because if you use the same controller for all loads, you you can design a controller that works for all loads, but the performance is not high because you need to design a robust controller that works for all of them. Therefore, the controller is conservative. Okay. So I'm explaining you what is the difference between fault tolerant control and the robust control. In robust control, we design one controller for all working points, but we design the controller to be robust so it is conservative. It guarantees the stability in all working conditions. But as I said, the performance could be actually affected. What is adaptive control? Adaptive control means that, okay, you have a structure, you design a controller, but the controller is parametric. For example, you have a PI controller, but the parameters of the PI controller can change along the way. So when you change the load, let's say you have a mechanism to find if the load has changed, and now you can retune or fine tune the parameters of the controllers online. We have such a controller, and it doesn't, by the way, it doesn't have to be a PI. You could design any controller. It could be a stable space, it could be even LQR, but the parameters of the controller can change when the parameters of the system changes. Okay, this one is called adaptive control. But adaptive control is different with fault tolerant control, because fault tolerant control, it's not a matter of changing the parameters. Let's say if this controller is not in the loop, this is the controller we have designed. Now a fault happens. When the fault happens, which means that you have switched the third valve off, it is not working. It doesn't matter how much you change the parameters of the controller. You will not be able to control the system because a sensor is gone or an actuator is out of order. Okay? You need to reconfigure the controller. And reconfiguration means that you need actually to change the structure of the controller if a fault happens. And in this particular case, changing the structure of the controller means that actually you should switch, you should have something here to switch actually between, to as I said, when the fault happens, then you can have another, let me have another switch here. Not this. So you have a switch here as well. I could have also bring this switch out just to, let me also do that. By the way, the valve, the input to the valve can be 0 because it is the linear input. Because when we set 0, it doesn't mean that the valve is closed because it is around the working point. And the working point for the valve, if you remember, was 0.5, which means that valve is 50% open, and now we are changing that. Okay, this is what we have in reality. So we have designed a controller which controls the level, the H2 using U3. The names are not correct. So again, I can run it. It would be the same result that we used to get. Now a fault happens, the valve is not working. If you run the same controller, it doesn't work. You're not able to control the output. You see that here is off. And what you can do, and by the way, I had this 0.3. Let me, if you want to get exactly the same result that we used to get, I assume that the valve has got stuck in one position, which is not okay. No, actually, the level is going down. Okay. Now, when the fault has happened, as I mentioned, you need to have a supervisor. It is called fault detection and diagnosis. It's a block that we will talk about that next week. And then the output of that block is that, okay, a fault has happened and where it has happened. And now we need actually to reconfigure the controller, and reconfiguration of the controller means that, first of all, you have to design a controller here, or you should have designed it in advance, and now you're ready to switch to that controller. Okay, now you switch and then you let it go. So basically you are able to control. But there is one thing here. The point is that if you have been connected to this controller for example, for 100 seconds, and the fault happens at that time, and you switch to the other controller, do you think a problem will happen? Do you think there would be a problem? Because here in the simulation, I don't show you that case that for 100 seconds, the valve number 3 is working and we have connected to that. So this control loop is working. And from 100 forward, then this valve is not working and we want to switch to the other controller. Do you think we should take something into consideration? Okay, I will let you know. I will let you think during the break, so we can take the next break and for 15 minutes, unless you have a question. Is there any question before we go to the break? Okay, so my question was, if for 100 seconds this the valve 3 is okay and it's working and it's controlling the level, and at that point we switch to the other one, not switch to the other one. I mean, this one is faulty, and now we get valve number 2 to work. Do you think there would be a problem? I have not simulated that here. When I switch, actually I switch at the beginning. So think about that. So I will be back at 11:10 or 11:12. 11:12 I will be back. 15 minutes break.